Hello students, welcome to the 41st lecture on particle physics. And in the 40th lecture, we have discussed two-flavor neutrino oscillation. And what I had told you that from two-flavor oscillation, we can generalize it to three-flavor oscillation. And what is important is that neutrino flavor states and when they are detected, they are different from the propagation states. And in the three flavor scenario, we have three flavors of neutrinos. We are calling it by the name nu e, nu mu, and nu tau always. And similarly, we could have nu e bar, nu mu bar, and nu tau bar, three anti-flavors of neutrinos. And here, instead of calling them by nu1, nu2, nu3, we could have called them as nu1 prime, nu2 prime, and nu3 prime by new names. And the important point is that flavor states and mass eigenstates, they are two different worlds. Flavor states is what you observe. Neutrino mass eigenstate is what they propagate, and a nu is electron type neutrino is some admixture of nu1, nu2, and nu3. Mu is some other admixture of nu1, nu2, and nu3, and so on. And therefore, if you recall, we for two flavor neutrino oscillation scenario, we wrote muon type neutrino state as an admixture of nu1 and nu2 in terms of the cosine theta and sine theta, and this we call it as theta as the mixing angle. And similarly for nu e, therefore for two flavor neutrino states, we had a simple matrix that was always that should be a unitary matrix to conserve particle number, and this we wrote something like this. This is nothing but the same expression, and then from here we obtained the survival probability of nu alpha that remains as nu alpha. And this is what I had told you, that this can be nu mu to nu mu, this can be nu e to nu e, or in general this can be any flavor e, mu, or tau. This is an important point, and this expression is not going to change. Important point that we have discussed, that theta equal to 0, there is no mixing. Neutrino flavor states are the same as the neutrino mass eigenstates. You can identify nu mu by nu1 and nu e by nu2. As you can put theta equal to 0, this fellow will go and this fellow will go, and you have you can identify nu mu with nu1 and nu e with nu2. It is only when you talk about theta you are talking about mixing. And then I have told you that one of the mass eigenstate has to be non-zero. It could be that both of them are non-zero. That is yet to be determined, that what are the exact values for delta m square, because for one that we will discuss, we have only determined the magnitude of that. Sign is still to be determined. Therefore, we don't know whether neutrino follow normal ordering or inverted ordering. Normal ordering means this is nu1, nu2, and nu3, and inverted ordering means this is nu3, this is nu1, nu2. It has been found that this guy is more than this. Therefore, here also that is true. But this fellow, whether it's lying at the bottom or it's lying at the top, this will be decided once we will determine the sign of the mass difference. Therefore, the important point is that there is a mixing angle, there is a finite delta m square, and then the oscillation, where will be the maximum oscillation, where all nu mu's will get converted into nu e's, all nu mu's will become again all nu mu's, that we have seen in the last lecture, but that will depend upon L by E. The important point which I mentioned in the last lecture, that this E for an accelerator experiment, this is if say 600 MeV, that will correspond to a certain L. If it is 2 JeV, it will correspond to another L. If it is 4 JeV, it will correspond to some other L. Therefore, the two flavor neutrino oscillation scenario, then we talked about the appearance probability, and that is what I told you, that this, if you remove this guy, this is nothing but giving you the probability of nu mu giving you nu e, or nu e giving you nu mu, or similarly for nu tau. And what I had told you, that this expression is not going to change whether you talk about electron to muon, or anti-electron to anti-muon, or anti-neutrino to tau type neutrino to muon type anti-neutrino. This hardly matters. Therefore, this expression, for this is what we call it as the appearance probability, and this we say that we can call it as disappearance probability. And this disappearance means how many have got converted into other flavor. Therefore, to start with, if I have 10,000 nu mu's, then we are observing something like 998. That means 9980 or 9990 or 92 or 94. We will say that 8 of them have got converted into either nu e, or 8 of them have got converted into nu mu and nu e together, if we are talking about three flavor neutrino oscillation. Therefore, if we have a nu mu beam, then it can give some part of nu mu to nu e and some part of nu mu to nu tau. But when you sum all the three probabilities, that should be equal to 1. Then instead of writing in this fashion, we introduce a unitary matrix, where we said that we have a neutrino eigenstate for the flavor, and this is the neutrino mass eigenstate, and this U is a unitary matrix, which is a 2 cross 2 matrix, and then we have the conjugate of that we talked about. And then when we switch to three flavor of neutrino oscillation, then we have nu e, nu mu and nu tau, and in other, they are the production states, or they are the particles which will be detected. But when they propagate, a nu mu will propagate as some mixture of nu 1, nu 2 and nu 3, and nu e will propagate as some other mixture of nu 1, nu 2 and nu 3, and similarly for nu tau. Therefore, the important point is, we have a flavor state, this is the mass eigenstate, and we are relating these two by a unitary matrix. This is a 3 cross 3 matrix, and the important point is that the overall, when we sum all the probabilities, this should be equal to always 1. Now, this matrix, the general form that one can choose, that is known by the name in general in the literature, is Ponte-Carvo, Maki, Nakagawa, Sakata mixing matrix. It was Ponte-Carvo who first gave the idea of neutrino oscillation, and how when neutrinos are coming from sun or atmosphere, they are changing its flavor. And initially it was for two flavors, and then it was generalized by Maki, Nakagawa, Sakata to three flavor neutrino oscillations. And here you can see that here, besides this cos theta, this C23 means cos theta 23, S23 means sin theta 23, S13 is sin theta 13. Therefore, initially for two flavor, it was just theta, whether you call it as theta 12 or 21 or whatever you wish. But here, when we are talking about three flavors, then we have to see the mixing of 1 and 3 and 1 and 2 and 2 and 3. Therefore, this is S stands for sine, C stands for cosine, and then this delta is the CP violating phase. And therefore, when you put all them together, this is the standard form of PMNS matrix, which generally people talk about. In this parameterization of the mixing matrix, the mixing parameters can take values in the range 0 and pi by 2 that we have talked about yesterday, and a delta which is non-zero, and this will cannot be 0 or pi, as you can directly see, and if they are non-zero, then that will lead to CP violation. If that is 0, there is no CP violation. That is pi, there is no CP violation. A non-zero value of delta or not equal to pi will tell us about the CP violations. Therefore, the parameters of the mixing matrix are determined in the oscillation experiments. The values of delta different from 0 and pi implies CP violation in neutrino oscillation in vacuum. Mind it, here I am introducing a term vacuum, where there is no matter. That means when a neutrino is traveling through Earth, you know that Earth is made up of matter, and therefore when it is traveling with Earth in Earth, then it may interact with matter, and the oscillation probability will change when you will take matter effects into account. Because if, for example, if we are talking about nu E coming from sun, then nu E interacting with neutron can give me E minus plus P, because we have seen solar neutrinos have energy up to around 50 MeV, and so therefore it is giving me electron. But if we talk about nu mu, then it cannot give me a muon, because muon mass is 105. Therefore, a nu E will interact through charge current interaction, while a nu mu will only it can interact through matter through neutral current interaction, that means through ZX0 exchange. While for electron type neutrino and electron type antineutrino, you can have W plus exchange or W minus exchange. Therefore, if we are talking about neutrinos coming from sun, electron type neutrino is going to interact with matter through charge current interaction as well as neutral current interaction. And therefore, when we take electron density into account or matter density into account, this oscillation probability that changes. And if you want to discuss them in detail, or you want to learn them in detail, you can see any book. For example, there is a book, The Physics of Neutrino Interactions. The Physics of Neutrino Interactions. This is by Cambridge University Press, and this is by myself and Skissing. There you will find all the properties of neutrinos and neutrino oscillation, neutrino sources. This book has discussed quantum field theory of particles, and then standard model of particle physics, Weinberg-Schlam model, and finally neutrinos, its production, its properties, then neutrino oscillation, and all that. Therefore, detail you can find in this book, The Physics of Neutrino Interactions. This has been published by Cambridge University Press, and you can find all the details that what happens when a neutrino interacts with matter. And this effect is known as, this matter enhanced neutrino oscillation effects in literature is known as MSW effect. M stands for Mikhailov, S stands for Smirnov, and W stands for Wolfenstein. These three people are scientists. they gave rise to the prescription that why in matter neutrino oscillation probability should change and what is that change. Therefore, when we are talking about the expression for the unitary matrix in the case of three flavor neutrino oscillation, then as we did for the two flavor neutrino oscillation case, here also when we are talking about the oscillation probability of one flavor to another, we have this expression, and then from here we can obtain the oscillation probability. Again, you see these all elements of these unitary matrices are what we wrote in terms of theta 1 2, theta 1 3 and theta 2 3. This is what is important, and then for a particular flavor you can similarly talk about mj square minus mi square. And when you write this expression in detail with the components where I is equal to j and then I is not equal to j, you will get these four terms. These are trivial and you can work them out. You will find that this is the general expression for the transition probability for a neutrino changing from a flavor alpha to a flavor beta in three flavor neutrino oscillation. Now what I am telling you that in the case of three flavor neutrino oscillation, there in the case of two flavor neutrino oscillation, you had delta m square and theta. But here you have delta m2 1 square, mod of delta m3 1 square that has been determined in the experiments, theta 1 2, theta 2 3 and theta 1 3, and then this delta, Cp violating phase delta. This is mass ordering, whether it should be normal ordering or inverted ordering. As I am telling you, that is a topic of research, that the sign will only tell you that what should it be, whether it should be a normal head ordering or inverted ordering. And you can see here this LBL stands for long baseline experiments, ATM stands for atmospheric neutrino experiments, REAC stands for the reactor anti-neutrino experiments, SOL stands for the solar experiments. Therefore, these are the different parameters which are determined in the different experiments, and that means using a long baseline experiment you won't be able to determine theta 1 3 or delta m2 1 square. Therefore, what I am telling you that LBL stands for long baseline neutrino experiments, and this we have talked about, that neutrinos that you are taking from Fermilab and the detect far detector is in South Dakota, or neutrinos you are taking at CERN and the detector is in Gran Sasso. Therefore, the oscillation length is quite large, while there are experiments which are short baseline experiments, and then you have the atmospheric neutrino experiments where the neutrinos are produced in the cosmic ray interaction of protons and alpha particles with the Earth's atmosphere, which give rise to secondaries like pions and kaons, and then they decay to neutrinos. Then you have solar neutrinos. The sun is the constant source of news throughout the year, and round the clock you are getting neutrinos from the sun. For using solar neutrinos, you can determine theta 1 2. Then combining long baseline and atmospheric, you can determine theta 2 3. Therefore, you can see that you can, from these looking at these sensitivities, and this we have discussed in the yesterday's class, you can see that there are different type of experiments. That means once you are doing accelerator experiments, you cannot leave solar neutrino experiments or reactor experiments, because these are sensitive to the different neutrino oscillation parameters. That is why simultaneously in this world we have reactor experiments, we have accelerator experiments, we have atmospheric neutrino experiments, we have solar neutrino experiments. Therefore, all these type of experiments are going on, and these are going on to determine the neutrino oscillation parameters. Now, if you uh, look at the different contours those have been obtained by the different experiments. Like here we are plotting, this is from a paper, sine square theta 1 2 on the x-axis and delta m21 square in units of 10 power minus 5 ev square. You can see that this is the black solid is from this solar, dash black is also from solar, this dotted is also from solar. But when this is large, black solid is large, as you can see, that means the confidence level here is large. Then when you are confining it, confidence level is small, and this is what they are talking about, the central value. And then from Camland experiment, you are getting a blue solid curve, the confidence level is say 99%. Then this dashed is the confidence level at 90%. This blue dot is the central value. Now you can see that if we combine Camland result, as well as Camland was a reactor experiment, and the solar result, we are seeing a region which is common to both, and therefore the chances of this delta m2 square and sine square theta 1 2 to lie in this region becomes large. That this is the highest probability of having delta m2 square and sine square theta 1 2 in this region. Now if you have many more experiments and then you come plot all of them together, all those experiments which are sensitive to these two parameters, more confidently you will be able to tell that what should be my delta m2 1 square and what should be delta and sine square theta 1 2. Therefore what is written over here, that 90% and 99% confidence level allowed regions in the sine square theta 1 2 delta m2 square plane obtained from the analysis of solar neutrino experiments, black line and Camland experiment. The combined is the colored magenta region. The best fit values are indicated with dots for the independent analysis and with a star for the combined solar plus Camland analysis. The reactor mixing angle theta 1 has been marginalized over without further constraint from short baseline reactor experiments. Then you have different accelerator experiments like NOVA, which is in Fermilab, T2K, which is in Japan, MINOS is again Fermilab. Therefore, these three experiments have independently measured delta m3 square 3 1 square on the y-axis and sine square theta 2 3 on the x-axis. So you see the y-axis has the magnitude. We still need a sign, and that is why efforts are going on. And you can see that the green line is for the MINOS, solid is for 90%, solid is for 99%, dash is for 90%. Similarly here, and then this green is the central value. Similarly, you see blue is for T2K, and this blue solid is with 99% confidence level. Dashed line blue is at the 90% confidence level. And therefore, what you are finding out that these are the different experimental constraints, those put limits on the neutrino oscillation parameters. And you find that the left hand side we have written NO and right hand side we have written IO. Left hand side represents normal ordering and right hand side represents inverted ordering. Therefore, the two ordering that I have told you, that which one should be lowest and what should be the hierarchy, presently these are the limits which we have obtained from the different experiments. Similarly, we have the limits from solar and Camland, the present limits, and the future when we have the Juno is again a reactor that is very promising. Then Dune experiment, which will be also sensitive to detect solar neutrinos. It is expected that this contour will further get confined and we will have better precision in measuring these oscillation parameters. Therefore, to see that we have a unity matrix which relates these two states. One is flavor states and another is mass eigen state. These are the present limits of the oscillation parameters. And in the next slide, and the last one on neutrino oscillation, I have shown here that what are the different limits of theta 1 2, theta 2 3, theta 1 3 for the normal ordering as well as inverted ordering. What's the value of CP violation that has been presently constraint that has been presently put both for normal ordering as well as for the inverted ordering. And you can see that best fit with 1 sigma standard deviation, 2 sigma standard deviation and 3 sigma standard deviation. You can see that these are the various parameters, these are the various limits, and the efforts are going on to put a better limit, to put a better constraint on these parameters. And we have traveled a lot in this area to understand the neutrino properties in the last 50 years, and many more efforts like Juno, like Dune, like T2 hyper K and many others, those are going on to understand neutrino properties. Now let's stop here. In the next lecture, we are going to talk about quarks, quark mixing, etc. Thank you very much.